Hey, I'm Alan Tsao, and let's dig into this second kinematics question that a student sent me. So you guys have sent me a lot of questions. I'm trying to filter it down, and I'll just pick one to do every week. This is just an example of a problem that you might be facing and how I would teach it to a student or how I would explain it to them. This is what I do for my students all the time. That allow them to ask questions offline and get a little bit of feedback on how to do a problem that they're kind of stuck on. So here we have a fugitive tries to hop on a freight train traveling at a constant speed of 6 meters per second. So we have this little train here, okay? And you don't have to draw a picture, right? You don't have to be as awesome as an illustrator as me, okay? So, boom. This is going to go 6 meters per second. And then just as an empty pass car passes him, the fugitive starts from rest. So now this guy's been going the whole time at the constant speed, but this guy's a fugitive, okay? So let's draw my little fugitive, okay? Cool. He stole a bag of money, right? So he's this is what he is. Some money here he stole. Okay, so he starts from rest and he accelerates at 4 meters per second squared to a maximum speed of 8 meters per second. So he's gonna move, and then it's gonna eventually go to 8 meters per second. And then there's a couple of questions. The question is this, so then, during this time, he's accelerating at 4 meters per second squared, right? During this motion from here to here, okay? And how long does it take to catch him to the empty boxcar, and what is the distance traveled to reach the boxcar? Okay, so now one thing you have to remember for kinematics equations is that the acceleration has to be constant during the entire motion, right? So we cannot allow us to use our kinematic equations whenever the acceleration changes, because once he reaches, and his acceleration has changed because once he reaches 8 meters per second, now his acceleration is 0 from here to here. So from here to here, he's going to be moving with the same 8 meters per second the whole time. And eventually, he should catch up because he's going faster than this cart. Now, there's a couple things that we don't know if this cart is if he's going to intersect while he's accelerating, or if he's going to intersect like after he's reached his max speed. He'll intersect at one point or another. So that's something we don't know. So let's pretend that, maybe it intersects like here, somewhere while he's accelerating. Okay, I'm just assuming that. I don't know that that's true. But you have to assume one way or the other. The other thing you could do is you could assume that he's actually over here. Like sometime. So we started here, and at some time here, they intersect, okay? They meet each other, and that's where that happens. So let's assume it afterwards. It'll be a little bit more complicated if it's afterwards here. So the thing about kinematics equations is you have to split it into different parts of motion when the acceleration is changing, okay? So in this case, what we're doing is we have to split it. We're going to talk about two motions. One motion from here to here while he's accelerating. This is motion 1, and then this is motion 2 of the fugitive. Okay, so there's two different motions that are happening there. And we use kinematic equations for those different motions separately. So let's say I set up the variables here. So the displacement, I don't know. The initial velocity, that's the velocity at the start. So let's identify. This is the start of the velocity. This is the initial velocity. This is the final velocity. Now, the final doesn't necessarily mean like, oh, hey, this is like, it's done moving, right? And the initial doesn't mean like the start of the universe, right? Like at the beginning. It's just the start of the motion and the end of the motion. So the initial velocity is 0 because he starts from rest. Yeah, he started from rest here. His final velocity here, if we say right is the positive direction, then this would be 8 meters per second. His acceleration is 4. And notice that with our kinematic equations, here's the thing, is that knowing 3 of the quantities allows you to solve for the other 2, right? So then we're going to use, let's say I want to find the distance. Basically what happens, in order for them to catch up, in the same amount of time, they have to cover the same displacement. So it's going to be the same displacement in the same time. So I'm actually going to need to know both the time and the displacement for this. Okay, so let's use this equation. V0 squared plus 2a delta x. So this is going to be 8 squared is 0 squared plus 2 times 4 times delta x. And now it's just a math problem. You can solve for delta x here. It's going to be 8. Okay, so 8 meters is how far he's traveled. So during this motion, we know it's 8 meters. And then we could solve for time using any of the equations we want. I like using this one. Because once you have 4 variables, like you can pick any equation you want to solve for the time here. So 8 is equal to 0 plus 4t, so the t is equal to 2. So that happens after 2 seconds. 2 seconds. Now, let's think about what happens after 2 seconds. In 2 seconds, this guy, he's going 6 meters per second. His velocity is not changing. He's doing 6 meters per second for 2 seconds, like a middle school problem, right? He's traveled 12 meters during this time. So in the same amount of time, he's traveled 12 meters. Okay? So therefore, during this time we've accelerated this 8 meters, we have not caught up to the freight car. If this number were smaller, if this number were like 6 meters, that means like, oh, in this time, this 2 seconds, we would have passed the cart. So we haven't passed the cart yet. So now we have to continue on. So now we got to talk about the second motion. Okay, let's think about what do I know at this point. Now in the acceleration, in this case, we know the acceleration is 0. And that means we know the start and end of the motion is 8 meters per second because he's at his max velocity. This is as fast as he's running. He's not going faster. If anything, he's going a little bit slower because like he's getting tired. But let's just assume he's going at the same speed at 8 meters per second there. Now here's the thing is I don't know the displacement, but let's say this is 8 meters. And let's say that let's give it a variable. Let's say that the distance it takes to intersect. Let's call that d and time t. We'll just call it, give it some variable names to just say like those are the things that I want. I want to know how far it took for this guy to go from here to here and the time it takes. So how far is this guy traveling? Well, if this is 8 meters here, then that means this distance here would have to be d minus 8. Right? Because this is 8, this is d minus 8, and the total distance has to be d. So this is going to be d minus 8. Okay? Now, how about the time? Well, whatever time it takes to go from there to there, it's going to take the time from here has to be t minus 2 seconds. Why? Because we've already spent 2 seconds accelerating. If I want this whole motion to take t seconds, and the first part takes 2 seconds, then the remaining has to take t minus 2 seconds. Okay, and now let's handle the cart. The cart is pretty easy. The cart is just, because its acceleration is 0, if you want to write it all out, and he's going 6 meters per second the whole time, his distance he's traveled is d, and this is t. Because for the train, or the empty car, he's just traveling that whole distance. And this one is pretty easy to relate. You just say displacement is initial velocity times time. But when the acceleration is 0, this term goes away. So it's just pretty easy. It's just d is equal to 6 times t. Right? Distance is velocity times time. Yeah, if the velocity is constant. All right? So then same thing for here. We're going to use the exact same equation for this guy, but we're just going to fill it in. It's going to be d minus 8 is equal to 8 times t minus 2. So what I know now is I have 2 equations and 2 unknowns, and I want to solve for both of them. So how do I handle that in math class? Is substitution is pretty standard. I'm going to plug this d into here. So I get 6t minus 8, and then I'll distribute the 8 there. It's going to be 8t minus 16. Move that over, that becomes 2t. Move that over, it becomes 8. So the t is equal to 4 seconds. So it took 4 seconds for the entire thing. And how far did we travel in the 4 seconds? 4 times 6 is going to be 24. So the d is going to be 24 meters. So it takes 24 meters and 4 seconds to catch up. Okay, so that's part A and B there. Now let's just verify like that works over here. So that means like this part of the motion was only 2 seconds. And he was traveling at 8 meters per second, so he traveled 16 meters. And that makes sense. So for the person, the fugitive, he travels 8 meters and 16 meters. That's 24 meters. And he does it in 4 seconds. Okay, 2 seconds for the first half, 2 seconds for the second half. I always just like to check my answers. They make sure they make sense. And this guy, for 4 seconds, he goes 6 meters per second. He also travels 24 meters, right? So that means they are going to be next to each other after 4 seconds there. So that's kind of the setup, right? The biggest thing is making sure you know how to set up all of those variables and set up the displacement, set up the initial velocity and the time. So I hope that was helpful. If you guys have any questions that you want to ask, any homework problems, no test questions, nothing that you're not allowed to like really ask about that go against your teacher's guidelines, you can send it to questions@bothellstemcoach.com. The email's in the description below if you want to. And I'll see you for the next one.